Hi, welcome to another edition of Calculus 2. Today we are going to start with a new chapter, and that's a chapter on infinite series. Fascinating topic. Let's go ahead and get this thing started. So, first section we are going to talk about sequences. There are many sequences that mathematicians are interested in, or engineers, and here we are going to take a look at some of the basic properties. So a sequence is essentially an infinite list of numbers. So most famous sequence, of course, the sequence of natural numbers, 1 2 3 4 5 and so on. Sometimes people like to start counting from 0, so it goes 0 1 2 3. Take these numbers and square them, you get another familiar sequence, 1 4 9 16 and so on. If you take 2 and raise it to consecutive powers, you get this sequence of numbers. These are the numbers you are very familiar with when you buy any kind of electronics. The number of gigabytes of RAM it might have and such is always reported to be one of these numbers. Next we have the so-called reciprocals of natural numbers. Then another sequence that has been famous in arts and biology and even stock market is the so-called Fibonacci sequence. It goes as 1 1 2 3 5 8 13 21. Can you guess who is the next one of these things? Can you detect a pattern that we are following, that you can guess what the next number is going to be? Well, think about it for a second. What do you think? From 3 and 5, how do you get an 8? Of course, you add the previous two, you get the next number. 5 and 8, you get 13. 8 and 13, you get 21. So the next one will be 13 plus 21, which is going to be 34. Another fascinating sequence is sequence of prime numbers. These are the numbers that have exactly two divisors. So if you want to break them apart, it's 1 times another number, which is just this number itself. How about this? Let's try our skill on this sequence. It's a sequence of rational numbers, 1/3, 2 7, 3 13, and so on. I am missing one here. Let me somehow. Okay, what do you think is the next number? Well, think about this thing for a minute or something. Come back and tell me what do you think this thing is. We have some clues here. Numerators 1 2 3 4 5. Most likely next number, well, has to be 6. How about denominators? You can go ahead and investigate what properties they might have in relationship to each other, and then you might see that, well, I have gone up by 4, then 6, then 8, then 10, so it makes sense for the next one to go up by 12. So the question of what is the next number of a sequence doesn't have a definitive answer. It's just by consensus as to what the next likeliest number is supposed to be. So what is after 1 2 3 4 5? Pretty much everybody agrees it has to be 6, but there is nothing written in law that the next number has to be actually 6. One way that to see this thing in a very loud manner is to go to one of the famous mathematical websites. It's called Online Encyclopedia of Integer Sequences. So this is where all mathematicians and engineers go to check a sequence of numbers that they might come across, to see if somebody has seen them before, in what context, what properties they have and such. So of course these are not like random sequence of numbers, rather they come out of a certain context. If you pay attention down here, you see that people have reported over 300,000 sequences here. So this database has 300,000 of these type of sequences. So if you are curious about a sequence of numbers you come across, let's say 1 2 3 4 5, suppose this is the one that catches your fancy and you want to see, well, what is this? Well, your first guess is that it's just the natural numbers. Let's see what does the website say. Well, the website agrees with you. The positive integers, so here the positive integers, he has written it from 1 through 77, and he has made the first few of them in bold to agree with whatever you had. But if you look closely here, you see it says 6,810 results found, meaning this is just one possibility that people came across. There would be 6,809 other sequences people come across, all of whom start with 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5 at least shows up somewhere in that sequence. So even though we say the next number is 6, it's not something that we are going to say, well, it's definitely 6. It's just by convention that we agree on that. Okay, so notation for sequences. Here I have already brought this issue up. The way we write the sequences, choose a letter for the sequence, and the position of the number in the sequence comes as a subscript. So we write this one as a sub n, and we write the formula that tells us what is the nth number of the sequence. So for example, when we come to squares, we want to know what's the fifth number. Well, 5 squared is going to give me the fifth number, and then I write a sub 5 is equal to 5 squared, which is just 25. How about this one? Well, this is the sequence that looks like somebody started counting from 0. You have two options. You can say an as 2 to the power of n, and n starts from 0 and then goes to 1, 2, 3. Or if you wish, you can write an, let's change the name here, maybe call it bn, and then this will be 2 to the power of n minus 1, and now you can start counting your n's as the usual 1, 2, 3, and so on. So when it comes to a formula for a sequence, you still have some choices depending on where you like to start counting. If you are starting counting from 0, you have one sequence formula, and if you start counting from 1, you have another one. So for this one, the sequence started from 1, so I write 1, 2, 3, and so on, and so on. So here for the reciprocals, we better not start from 0 because it's going to give us some problem. So in this case, we say n starts from 1, 2, 3, and so on it goes. Fibonacci sequence. Fibonacci sequences, well, we are going to come across this thing later on. The formula for the nth term is not easy, but the description of a sequence as each of them in terms of sum of the previous two, that is easy to describe. Such sequences are referred to as recursive. Recursive means you have a formula that tells you what is each number in terms of the previous numbers. So for Fibonacci sequences, when we want to say it's the sum of the previous two, well, the one prior to n is n minus 1. The one prior to that one is n minus 2. So that is how they are generated. And then you specify the very first two so that you jumpstart the sequence. So such a description always comes with some starter value. So we would say f1 is 1, f2 is equal to 1 also, and starting from 3, then the rest of them comes out of this recursive formula. So our formula is good for n larger than 2. Prime numbers. Prime numbers, well, this is something that you come across starting from middle school, perhaps elementary school. This is even more mysterious than the ones that we had seen before. What's the formula for the nth prime number? Well, that is a very tall order. We neither have a formula of that sort nor any easy description of what the nth prime is. It's just we eliminate all the numbers that are product of two other numbers, and then whatever is left is going to be labeled as a prime number, and no easy way of catching them. Okay, let's go and say a few more words about the notation that we had here. First of all, a sequence is really a function. It's just a function whose input is the set of natural numbers. So sequence is a function, and we could write it as f with the parentheses in, but the convention is to simplify this thing, get rid of the parentheses and move the n down here as a subscript and write it as f sub n. So for example, if you want to talk about Fibonacci sequences, we typically use capital F for that. It's the name of somebody. F sub 1, F sub 2, F sub 3, and so on. And then, as we said, F sub n is equal to the sum of the previous two F's. Okay, what is of significance for us is the notion of a limit of a sequence. So limit of a sequence, we have to go back to calculus 1. We have the concept of limit there, and a lot of stuff that we are going to talk about here are going to be essentially copies of whatever we had in calculus 1. No surprise, because sequences are really just functions. Let's go ahead and try to make sense of the following. Suppose I have a sequence, let's call it f of n, and I want to investigate what do I mean by limit of this as n goes to infinity. What is the meaning of limit of a sequence as n goes to infinity? Let's pick a simple example. Suppose I take f of n to be 2n divided by n plus 1. So here is a formula for a sequence, and the question is what happens to this thing as n goes to infinity. A variety of ways can be used to arrive at that limit. Very first thing that perhaps you want to do is just try out some numbers, see what happens. For example, we want to pick n here and see, test the waters. Essentially, n is supposed to go to infinity. Of course, we can go to infinity like 1, 2, 3, and so on. That goes to infinity. But sometimes you might accelerate that process a little bit, go through 1, 10, 100, 1000, and so on, so that the picture emerges faster. All of them go same place. Some of them go there faster than others. So if I put 10 here, I get 20 over 11. Okay, so if n is 10, I'm looking at f of n is 20 over 11. What if I put 100? Well, I'm looking at 200 over 101. How about 1000? Well, I'm looking at 2000 over 1001. Well, if you were asked to quickly do an estimation for this thing, what would you have said? What is the approximate value of 200 over 101? Or what's the approximate value of 2000 over 1001? Say you don't have a calculator or something, you are pressed for time and you want to give a quick answer. Well, this is almost twice as big as that. If you ignore this little 1 here, it looks like as we march toward infinity here, this thing marches toward 2. That is the holy grail of calculating limit of a sequence. How do we come across that? Well, let's go ahead and do some simple exercises, and then we are going to come back to the definition of limit. If you have gone through this thing in calculus 1, you remember it was a tough topic to get used to the notion of the correct definition of limit. So let's start by some simple approaches to this, and then we come to the definition itself. So you remember we had some rules of limit that were presented in calculus 1, and exact same rules apply here. So rules of limits of sequences. Well, let's pick some sequences and suppose we have investigated them and figured out what the answer of each of them might be. So suppose I have one sequence, I call it AN, and another sequence I call it BN, things like this. And suppose we have worked out what the limit of the first one is supposed to be, let's call it capital A, and the limit of the second one, suppose we have worked that one also, and we have figured out that that answer is B. So AN and BN, like this example, and we have somehow arrived at a certain value for the limit, and the question is, well, can you construct anything out of these? Well, yes. If you were being asked to figure out what's the limit of AN plus BN, what would you say that is? Well, it's almost instinctive, even though it requires a proof, but the limit of the sum is the sum of the limits. That is, this AN goes to A, BN goes to B, and the sum is just the sum of the two limits. And if you were doing subtraction, well, it would be subtraction of the two limits. But if you were multiplying, suppose you were taking ANs and doubling each term, what would be the limit of that? Well, if everything doubles, the final answer also going to double. So limit of that when n goes to infinity is 2a. Nothing special about 2. If it was a 3 or 4 or minus 5, same thing is going to happen. So we might as well write the general term here, and the way they write it is, okay, if I have any constant c and I multiply it by terms of my sequence, my limit is going to behave that way. If I have an multiplied by bn and I want to find the limit, it's simply product of the limits. And if I want to take a ratio, assuming that I could take the ratio, well, what could prevent me from taking ratio is that I shouldn't ever be dividing by 0. And the answer to this is also the ratio of the limits, provided that, well, that one is also not 0. So these are some basic limits activities that are exactly mirroring what you have seen in calculus 1. Over there, this would be f of x and g of x and so on, and we're just changing the notation a little bit. Let's go ahead and practice this in a simple example. Suppose I have an defined as, say, n squared plus n plus 1 over, say, 2n squared plus 3. Question is, what is the limit of this? Limit of an as n goes to infinity. This problem is also a copy of a problem in calculus 1. Over there, it might have been presented to you like this: f of x is x squared plus x plus 1 over 2x squared plus 3, and the question might have been, what's the limit of f of x as x goes to infinity? If you can find a limit for this in calculus, then the limit of this will match exactly what you had over there. So if this is meaningful and you can find the limit, then whatever method you applied there is applicable here. Whatever answer you had there will be applicable here as n. So how would we have conquered this problem in calculus? We go ahead and typically divide by the largest exponent in the denominator. That is applicable to all these rational functions. So we take an and divide everybody in numerator and denominator by Largest power we see in the denominator, so in this case is 2n squared plus 3. Okay, so dividing numerator and denominator by same number doesn't change the fraction. Then I break it up into 3 pieces, so n squared over n squared is 1, n over n squared is 1 over n, 1 over n squared is 1 over n squared. 2n squared over n squared is 2, and this is 3 over n squared. Okay, now we appeal to a certain fact that we had in calculus 1 as well. If I ask you what's the limit of 1 over x when x goes to infinity, what would you say that answer is? 1 divided by a large number. Of course, that is 0. Same thing applies to limit of 1 over, let me write this thing separately so I don't cause a misunderstanding. If I had limit of 1 over x squared when x goes to infinity, that's also 0. So long as you have a positive exponent on x, it all goes to 0. So now we can say limit of an is same as the limit of this expression. That limit is limit of numerator divided by limit of denominator by using this fact. Now limit of numerator is sum of several limits using this fact. This is sum of limit of 1 over n, limit of 1 over n squared. Well, 1 over n squared go to 0. So limit of this becomes 1, 0 and 0 divided by limit of 3 over n squared. Well, 1 over n squared goes to 0. If you triple it, still goes to 0. And out comes 1/2. So limits of rational function is very easy. You just consider the ratio of the so-called leading term, and that is going to tell you quickly. Let me see if you can answer some other examples by yourself quickly. Suppose I define Bn to be, say, n plus 1 over 2n squared plus 3 again. So I'm skipping n squared, I have just n plus 1. What's going to happen here? So we learned how to approach it here. We divide by n squared. This becomes 1 over n plus 1 over n squared, and denominator becomes 2 plus 3 over n squared. Now if I want to write limit of Bn, denominator as before is just 2, but numerator, that 1 is missing, and 1 over n and 1 over n squared, both of them go to 0, so I get 0 over 2. So lesson to be learned here is that if the degree of numerator is less than the degree of denominator, then the limit is going to be 0. Let's try another example. Suppose I have Cn, and this is, let's keep it simple, n cubed over 2n squared plus 3. So if I'm investigating this, again, I divide by n squared, so n cubed over n squared is just n. Denominator is 2 plus, well, 3 over n squared. So when I ask what is the limit of Cn, what would you say it is? The denominator goes to 2, but numerator is going to infinity, and is going to infinity, this is going to infinity, the ratio becomes infinity. So let's quickly recap what happened. If the degrees are the same, the ratio of the leading coefficient, that's what your limit is. If numerator has degree less than denominator, the limit is 0. If numerator has a degree more than denominator, the answer is either plus infinity or minus infinity, depending on the sign of the coefficients that you have here. Okay, we experimented with some simple examples. Let's go to some advanced example and something that we skipped because it's rather tricky. Well, what do you really mean by the limit of a sequence? Let's go ahead again, start easy by some graphical presentation, and then come back and see what we can make of this thing. Let me write down the definition of the limit before we so we say limit of a n as n goes to infinity is some quantity, let's call it L for limit. If given any epsilon positive, there is a n, there's a number n such that difference of an from that limit is less than epsilon for any n larger than that capital N. Okay, if you have come across the definition of the limit in calculus 1, you know that it was a hard cookie to chew on, and it was quite a surprise. If you haven't come across it, well, it's going to be an even bigger surprise. Don't feel too bad about it if you struggle to understand what does that sentence say. It took mathematicians from around 16th century, so 17th century to 19th century, a span of about 250 years to settle on this definition. So if something took 250 years for mathematicians to summarize, then well, it's justifiable that we have a bit of a hesitation with trying to understand what that thing is. So let me try to see if I can explain it to you in the context of a picture. So let's go here. So Desmos is a very nice software for this kind of things. Let's see if we can explain the phenomena here. So I'm picking some function fn equal to 2n over n plus 1. So that could be our sequence. The sequence will be f sub n here. That's how we write it. Fn is equal to n over n plus 1. The graph of the function is this red curve. If you just pick whole numbers 1, 2, 3 and so on, then you are going to get these circles. So for example, if n, I pick it 1, I get 2 over 2, which is equal to 1. So you see I'm at the height 1. If I take n to be equal to 2, well, then I have 4 over 3. 4 over 3 is 1.33. This is showing that we are there. If n was taken to be at 3, so 2 times 3 is 6, 3 plus 1 is 4, 6 over 4 is 1.5, and that's where we are. So for each of those whole number values for n, I get one of these circles. Okay, where is this thing going? We said we have to take the limit as n goes to infinity. You see, if n is this number, 14, 16 and so on. As I go further and further out, these circles are inching up toward a certain line. That's the line that we call the limit. Our limit, we said, is equal to 2. Now the question is, well, how does that get established that the limit is 2? Sometimes, especially in an introductory class, they say as the function or as the sequence comes closer and closer to 2, that manner of trying to simplify the definition of limit is not really correct. It causes some problem. I'm going to explain to you what that problem is. What is the true definition? The true definition is exactly what we wrote here. There is no way of simplifying this. If there was a way, during that 250 years somebody would have come up with one. So even though in some introductory lectures they might try to say this thing in a way that doesn't sound as peculiar as it is, none of those attempts are actually going to work. What is the definition? Let's go ahead and take a look at here. So we want to claim that the limit is 2. How do we establish that? And what does that mean? There is an epsilon. If I change that epsilon, you see that band widening or narrowing. The game we are going to play is the following. I give you an epsilon. So the game starts with this. You claim it is 2. I demand demonstration. The demonstration goes like this. I'll give you an epsilon. That epsilon creates this band. Let's think about this band as a trap. Okay, as a trap, and these values of the sequence as an animal that perhaps trying to avoid that trap. Now, I take this sequence of points and then I start going through them. This 1, I color it green. 2, 3, I color them. You notice that at some value of n, my points enter inside trap and then they forever stay inside that trap. Well, that means in the first round you win and you have partially established that the limit is 2. Now I make the problem harder on you. I make the trap even smaller, so I make it like narrow, quite narrow. What now? Well, suppose I make the band as narrow at 0.1. Now you have to go out, way out. We have to keep zooming this thing, and then it becomes hard to see. At some point, these points of the sequence enter the trap, and that is where you get validated for your claim. So the narrower the trap is, the further out you have to go to stay in that trap. If you stay in the trap after that point, then you have partially established that the limit that you have guessed is correct. The game, however, never finishes. That is, I can make the trap smaller and smaller, and for each size of that trap you should be able to come up with a location of n such that after that the animal enters the trap and never gets out. Okay, now let's go back to the definition that you might have seen in calculus. Somebody might have said it comes closer and closer. The elements of a sequence come closer and closer to some value. Is that correct? Let me make it wider so that we can see. Let me change the sequence. Suppose I write 2n times sine of n. Well, in this case you see that there are some dots that are getting close, but then there are lots of others that are staying far away. So just having one element inside of a trap is not a big deal. If the creature gets out again, the whole bet is off and you don't actually have established anything. Let's go to something else to also dispel another assumption. I write 2n plus sine of n over n plus 1. This one, the limit is still 2, but what happens is that the creature comes inside the band but then gets out. It goes inside. Now it does what we want it to do. It stays inside the band, but as you see, it comes close but then it moves away. It comes close and then it moves away. The limit is still 2. It's just that the thinking that our numbers are coming closer and closer, that just doesn't work here. It does not come close in a uniform way. It comes close, goes away, comes close, goes away. Overall, yes, it's getting to use the incorrect wording. It comes closer and closer, but that concept really doesn't pan out. So there is a reason for this definition. You have to read the text, some maybe beginning of a calculus text, to see the subtlety of this. We are going to set it aside because going after that might overwhelm us. So most of the examples that we are going to go after are going to be treated without using this so-called epsilon n definition of the limit. But I just wanted to bring it out so that we know that there is some difficulty in the concept of limit. We don't want to make light of it. Well, what was the practical way of finding limit in calculus? One of the powerful rules that we had over there was Hopital rule. So practical we had a so-called Hopital rule. Let's explain that in the context of an example. Suppose I have a sequence, and that is, say, n squared plus n plus 1, say, over exponential of n plus 1. Again, the question is, what's the limit of this as n goes to infinity? Just to remind you that you have seen problems like this thing back in calculus, let me go ahead and use the notation of calculus. Over there we used to have a function with the input of the function written in this manner, and then this is probably what you would have written there. As we said, if the function has a limit, then the limit of a sequence is going to match this. Well, how did you find the limit in calculus 1 as x goes to infinity? L'Hopital's rule said, well, take a derivative of this. Derivative of numerator is 2x plus 1. Derivative of denominator is e to the x. Well, we still are dealing with a limit to be taken. L'Hopital's rule told you that you can actually repeat this process as many times as it takes. If the final round you have a limit, then the initial function matches that limit. So in this case we are going to take a limit a second round, so this is going to be 2 over e to the x. What did I do? Derivative of 2x plus 1 is 2. Derivative of exponential of x is just exponential of x. Now 2 divided by exponential of x. Exponential of x goes to infinity. This is a constant. A constant divided by infinity will be 0, so this limit turns out to be 0. So if the L'Hopital's operation ends with a definitive answer, then you can borrow that and use it here and say, okay, the limit of this is equal to 0. One general idea that makes this problem a lot faster is that the polynomials are always gonna grow a lot slower than exponentials. So if you have a match against between these two type of functions, polynomials versus exponentials, exponentials always dictate what the answer is going to be, and you can guess what the final answer is. Okay, before we close this section, let's introduce one function that shows up in our discussions very often, and that's the so-called factorial functions. Factorial, most of you again familiar with it from calculus 1, but let's just go ahead, refresh our memory. Factorial function, in many examples we come across particular kind of multiplication, such as 1 times 2, 1 times 2 times 3, 1 times 2 times 3 times 4, and so on. We want to have a notation so that we abbreviate this kind of writing. The notation is simply write the number followed by an exclamation and read it as 2 factorial. So this is going to be 3 factorial, this is going to be 4 factorial, and of course it's obvious this is 2, this is 6, this is 24, and so on. So n factorial, when we want to write n factorial, means multiply all the numbers between 1 and that number n, that would be n factorial. For the case of 1 factorial, we don't have any multiplications, just number 1, and that is just 1. Standard convention that helps us in many of our formulas is to define 0 factorial. Okay, 0 factorial doesn't match the description, but by definition we set it to be equal to 1 just for simplicity of our future formulas. Notice an issue. In investigating this problem, it was easy for us to say, okay, n squared is particular value of x squared. Okay, if I have a squaring function, if I choose whole numbers in it, well, then I'll have n squared. The issue of what is x factorial, that's a very complicated question. That's also another question that took mathematicians a very long time, and you are going to see that in some advanced mathematics classes. We are not going to introduce you to this. This relates to something called gamma function. So that's going to create a challenge for us, because if our problem has a factorial in it, we cannot easily go to a function that copies that value without going through some advanced topics. So we are going to have some alternate ways of handling some of these problems. It's going to be a bit more complicated than the problems we have done so far, but I'm sure we can all do it. Before we come across those advanced issues, let's make it clear as to what our notation is going to be in this case. So you remember in pre-calculus or algebra, when you came across an expression such as this, there was the issue of order of operation as to what do we do first. Do we multiply first or do we exponentiate first? So over there we learned that exponentiation always trumps multiplication. So this has to be understood as 2 times x cubed. Well, what if you actually wanted to multiply 2 and x first? In that case, you had to use the parentheses around 2 and x to make it clear that you want to multiply first. Same issue comes with the factorial. So if I write 5 times 4 factorial, I do not mean multiply 5 and 4 first and then take the factorial of that. No, what I mean is factorial goes first. 5 times 4 factorial. So factorial 4 factorial would have been 24, so 5 times 24, and the answer would have been 120, which is actually the 5 factorial. What if I wanted to do it the other way, 5 times 4 factorial? Well, I had to use the parentheses, then I would come across 20 factorial, which is a humongous function, humongous number. In fact, you can go on your calculator, play with your calculator button. There's always a factorial button there. You can play with that and see that it's a monster function. It grows very rapidly, and we are going to be talking about that rapid growth in some of the problems. Just let me finish with one simple way of handling these factorial functions. Again, not an easy description here, but we have no alternative to it. So the question is how to understand the behavior of the factorial. One way is to compare it against the exponential. So here's a question. Compare 2 to the power of n versus n factorial. Well, how do you compare? Make a table. Here I'm making the table. So n 2 to the n and n factorial. So 0 by convention, you remember this is considered to be 1, and by convention this one is also considered to be 1. 1, this is going to be 2 to the power of 1, and 1 factorial is just 1. 2 to the power of 2 is 4. 2 factorial is 2. You notice this is beating that, this is beating that. 3, 2 cubed is 8. 3 factorial is 6. 4, this is 16, but 4 factorial, 1 times 2 times 3 times 4 is 24. We see that the competition is resulting in a different kind of an outcome. Here at the beginning they were the same. For a few cases we saw that in these cases 2 to the power of n is larger than n factorial. Here they are the same. After that, meaning for majority of cases, 2 to the power of n loses to n factorial. It's very easy to see why, because every time here you are multiplying by just 2, but with the factorial every time you are multiplying by a much bigger number. So from here to here you are multiplying by 4, then you are multiplying by 5 and 6 and so on, but here you are always multiplying by 2. This is you are multiplying by number that is growing, this is you are multiplying by number that is fixed. So 2 to the power of n is going to be less than n factorial. And in fact you can use this argument to show that limit of 2 to the power of n over n factorial as n goes to infinity is 0. How do we see that? So here was the argument that the limit of 2 to the n over n factorial as n goes to infinity is 0. Let's write it like this. 2 to the power of n, what does that mean? So that was 1 times 2 times 2 times 2. So let's separate the first 3 of these things and then the rest of them. So this becomes 8 times 2 to the power of n minus 3. Of course, that is exactly the same as that. How about n factorial? N factorial is 1 times 2 times 3. Then after that it starts with 4 and 5 and 6 and so on all the way to n. Well, each of these numbers is at least 4. Is that right? The very first one is 4, and the next one is bigger and bigger and bigger and so on. So 1 times 2 times 3 is 6, and all of these numbers are 4 or higher, so this is going to be more than 4 to the power of n minus 3. Okay, let me write this thing clearly. Now if I take a ratio of these two, 2 to the power of n over n factorial, you see that is my denominator is going to be bigger than this. Therefore my fraction is smaller than this fraction. Eight over 6, you can now put it on the side. This one you can simplify it. 2 to the power of n minus 3 over 4 over the power of n minus 3. That's going to be 1/2 to the power of n minus 3. So for n larger than 3, 2 to the power of n over n factorial is less than that. This is a result that we are going to use often. So let me summarize. For n larger than 3, 2 to the power of n over n factorial is less than 86 times 1/2 to the power of n minus 3. Well, what does that tell us? That tells us that the limit of this ratio, or limit of 2 to the power of n over n factorial, when n goes to infinity, is going to be less than or equal to the limit of 86 of 1/2 to the power of n minus 3, and 1/2 raised to large exponent is going to be a small number, and this quantity is going to go towards 0. So that establishes the fact that we stated here 2 to the power of n over n factorial is going to have a limit that's equal to 0, essentially telling us that exponential is going to be much smaller than the factorial. So factorial function, as we mentioned before, is a kind of a monster function. It grows a lot faster than other functions we have seen before. As a result, if you have an exponential divided by a factorial, the limit will be 0. Okay, so the end of the lecture was a bit complicated as we talked about the factorial function. Things are perhaps a little bit unfamiliar, but as you do the exercises, you will get used to it. Until next lecture, good luck and God bless.